notes in front of you, but if you feel that you can take down some handwritten notes, please do so. Okay? So this is part 2, second part of the lecture for today, continuous time systems. This is a usual definition for Laplace transform. I'm not going to go through it again. So any derivative, alright, dy over dt, that we transform into equals to response s ys minus y to the initial value. Okay, and likewise, okay, if you have a system which is dn yt over dtn plus a over n minus 1 dn minus 1 yt over dtn, etc., you can still take Laplace transform. Alright? And you can transform this into s to the power n ys plus a n minus 1 s power n minus 1 ys and so on and so forth. Okay, so this is transforming from a differential equation into recursive response. You can look at it in terms of a transfer function. Okay, you're very familiar. Ys is gs us. Alright, so y ys gs times us. Okay? Yeah, and very often, yeah. Okay, thanks. All right. Now, very often we say that transfer function is output over input. This. Okay? And what is G? What is G? All right, if you recall our previous block diagram, which is extremely important, we always have a reference. Yeah? We have a controller, C, the plant, G, which you used to call output Y. Okay, then you feedback the arrow E over here. Okay? And what's the output of the controller is U. Alright? And the controller gain, if it's just proportional, is K, so U is just KU. This is what you learned in Dynamics and Control 3, right? Okay? And now we tell you that if you have n derivative, so G is just y over U. It can also be written as Bs over As. Okay? And what is As, what is Bs? They are just polynomials. Okay? What's a polynomial? A polynomial is s to the power n plus something s to the power n minus 1 plus something s to the power n minus 2, and so on and so forth. Alright? Gs is just a polynomial. So, polynomial function. Okay? So, an example of Gs can be just 1 over s plus 1. It's just a polynomial function. Yeah? Okay? Gs can also be s to the power n minus 1 over s to the power n plus s to the power n minus 1. Yeah? It's just a polynomial function. Okay? These are just examples. Alright? In addition to looking at it in frequency response, you can look at it in time domain as well, right? I just said that we're going to cover some sort of state space over here. Okay? So if you have a system let's do it. Okay, this is just explanation. Yeah? If you have a system dx okay, dx t over to t, which is axt plus dut, okay, and the initial condition 0 is alright, and the output y is cxt plus dut. Okay, how do you transform this? How do you actually identify the transfer function g from this? Okay? This is a revision lecture, it's going to get a bit dry. What you do first, for the first equation, we have S, yeah, minus 0, just A, XS plus B, US. Alright? The second equation, so YS, C, XS plus B, US. Okay? So from equation 1, there's XS on the left, XS on the right. Shift them together. So S, XS, minus A. S. Do the initial condition inside. That's yeah? Factor out. Alright? Because X, I will tell you now, don't just look at X as a single variable. Okay? So it can be a multi-variable. Alright? So we look at SI. I for identity matrix. Alright? Minus A, XS. X, not plus US. Okay, and what's XS? So XS is inverse of SI minus A. It's not plus inverse of SI minus A. Okay. Alright, and what is Y? What is the output? YS will just be substituting XS back into equation 2. So substitute this as equation 2. We got C of SI minus A inverse X plus C of SI minus A inverse B US plus B. Okay? Alright? There's US here, there's also US. Group the US together. So you have, yeah, quite bigger. Okay? C. Sorry, our first lecture for this term, I also need some calibration. Okay, C, S, I, minus A, inverse B, plus B times US, plus C, S, I, minus A, inverse X. Alright, and what is this? This is your ratio, right? Your Y over U. Alright, so this is your G. It's your closed loop transfer function. Okay? Alright, so that explains to you why on the slide you see that GS is C SI minus A equals B plus Alright, very basic. Let's move on. Okay. In summary, transfer functions describe the input-output properties in algebraic form, meaning polynomials. Alright. And we look at we are concerned about stability transfer function. So how do you know if a transfer function is stable? Alright. Because the transfer function GS is output YS over US, right? So that's output is equal. I would say that the system is always stable if a bounded input, a bounded U, produces a bounded output. Alright? For all bounded initial conditions, for all x0. Alright, then we say the system is stable. Okay? And in particular, if you have a transfer function, GS, which is 1 over, let's say, like 1 over S plus 1 plus S plus 2, you can break it up into partial fractions. Okay? to tell how the roots will behave of this transfer function, right? So if you have, you are done with this, huh? Okay, if you have GS, example, GS is 1 over S plus 1 times S plus 2. Okay, you can break this up into partial fractions, right? So you can substitute, carve out S plus 2, carve out S plus 1, substitute minus 1. Yeah? So 1 over 1, so it's 1 over S plus 1. Okay, and then carve out plus 2 substitute minus 2 minus 1 over S plus 2. So you break it up into two portions. Yeah? Partial fractions. From there, you can do an inverse Laplace transform for your y, right? So you know that it's exponential to the power of minus t minus exponential to the power of t. Example, yeah? And what do you realize? You realize that if you solve the denominator here, s plus 1 times s plus 2 equals to 0, s is minus s plus 1 plus s plus 2 equal to 0, the characteristic equation for the solution. S equals to minus 1 and s equals to minus 2. And these are strictly negative. Alright? I would say that the poles have strictly negative real parts. Alright? That's what it means by. For continuous time system, we say that stability requires the poles to have strictly negative real parts. It means they have to be on the left hand side. Okay? Alright, so summarize again, there are these two approaches. We can either time domain for differential equation, then you write some space function which relates to your transfer function, or you can look at it in frequency domain, pure S terms. Alright? And these two approaches are actually equivalent, but they have advantages to each of them. There's also a reason why we sometimes look at systems in time domain and sometimes in frequency domain. Alright, particularly in time domain, we look at systems as differential equations. Alright, and we look at how they evolve over time. So take for instance this one. Okay, if your input is just a step function, then you can break this down and say that yt is e to the power of minus t plus e to the power of minus 2t. When t tends to infinity, what happens to y? 0. Huh? Y is e to the power of minus t minus e to the power of minus 2t. So when t tends to infinity, y goes to 0. Okay? So this means by, this tells you that know how the variables evolve in time. Alright? And we computed by solving simple differential equations. Meaning, if you have a differential equation, p xt over dt equals to some xt plus some ut and yt equals to some xt plus some ut, you can come up with the transfer function. Yes? You can solve for the poles. Then you can write what is yt exactly, and you can see how it behaves over time. Alright? What about frequency domain? Okay, in frequency domain, we always draw a block diagram. Yes. Alright? You say that input is always y, u, and output is always 1. Okay? And we look at how the transfer function behaves. Alright, what do you look at? In terms of G, we look at two things. One, the gain of GS, and the phase of GS. All of you know this very well, at the end of phase. Okay, and what is S? For S, about a certain frequency. Okay, so if your U is a sinusoid, a certain frequency, and it goes into your G, and G is stable, bounded, output Y will be of the same frequency. And it's also if your U is a sinusoid, what's your Y? If your U is a sinusoid, then your transfer function is 1. What's your Y? Sinusoid. Okay? Exactly the same. Unless your G is e to the power minus t, meaning you take the sinusoid, multiply by the decay function. So your y, of course, will be a sinusoid. Okay? Okay? Alright? So if you have a transfer function G, we also look at the poles. And we say that with respect to stability, the transfer function is stable if and only if the real part of all poles are strictly negative, and if they are on the left-hand plane. If one pole is on the imaginary axis, what do you call it? Marginally stable. Alright? If one pole is on the right-hand plane, unstable. Okay? If you look at the phase, you have non-minimum phase, meaning the real part of x1 is 0, strictly positive. Okay, before non-minimum phase. Alright, so we don't just, in this module, we don't just look at poles, we also look at the solution of the numerator. Okay? So remember, we'll just say that the transfer function GS, now if we look at it, it's just ES over AS. Okay? That can be a numerator of ES, which is a polynomial, a denominator AS, which is another polynomial. Okay, so the solution of AS will give you the poles, and the solution of BS will give you the zeros. Okay, further revision, impulse and step responses. Alright. A lot of words over there, but just as a quick revision, what is an impulse response? So impulse response is when ut is delta t. Okay, when ut is delta t, in Laplace transform is just 1. Okay, but input is impulse. Okay, and what does it mean? Our output y, which is gs us, it means that this is just gs. Okay, step response, something like this, straight step response. For instance, example is just 1. ut is just 1, us is 1 over s. Okay, and ys, gs over s. Okay, impulse response is that. Alright, how does the impulse response look like? If you look at that slide, basically area under the curve, you take 1 over delta, and delta is 1. Alright? Okay. 1 over delta and delta, the triangle is delta. Over delta times delta, area is 1. So impulse is anything that's area 1 and it's in a very short time interval. Okay? Alright. We're going to say what is steady state step response. Okay, you can see that this is the final value theorem. Yeah? Still remember final value theorem? Okay? Final value theorem. The limit as t tends to infinity of yt is a steady state. Y infinity. Okay? And this is v of s tends to 0. S times gs. Okay. I think it's just final value. Okay, what's the final value? So if you have step function in some dynamics, like for instance this, like that. Okay, final value theorem will give you the final steady state value of y infinity. Okay, understood? And we can define the following indicators. Alright, first of all, the steady state value, which is your y infinity. Okay, we can define rise time. Rise time is the time taken to rise from 0 to about 0.9. The steady state value is sometimes 1. So according to different control textbooks and different definitions. Okay? Overshoot What show is how much you exceed the steady state value. Alright? We also talk about undershoot, how much you fall below the steady state value. Okay, and sampling time. So sampling time again, how much time you need to reach somewhere in the vicinity of the final value. And this definition varies from person to person. Alright? Okay, this is a typical shape of step response. Okay, so far so good, step response.